Yeah, now we're going to talk about bond enthalpy. Okay, how much energy is actually released by bonds? Similar to Hess's law, this is a method of taking bond energies that we know are in reactants, breaking them apart. When we break them apart, we can figure out how much energy is in the reactants and how much energy is in the products. So we know from experimentation that if we do something like take hydrogen, okay, and I zap it with energy, it's going to break into hydrogen atom gas, okay, both of these are gaseous, plus another hydrogen atom. And when I blast those things apart, they're going to have a specific amount of energy that's associated with that bond. And in this case, for hydrogen and hydrogen, what we get is 436.4 kilojoules per mole. Is it 434 or 436? 436.4 kilojoules per mole. Okay? Now that's great for our hydrogen. It's kind of useless in our experimental mindset because the only thing that's got a hydrogen bond is hydrogen gas, right? So when we're looking at more complex molecules, we're looking at how much energy is associated with each particular bond. Fortunately, you guys don't have to calculate this. This has been done experimentally by a lot of really smart people. Okay? And there's a table, and there's tables in your book that give specific bond energies for each one of these things. Okay? It's like nitrogen and hydrogen. If I have one of these, okay, the bond energy that's associated with this is 393 kilojoules. What that means is that if I have NH3, the total bond energy that's inside of NH3 is going to be 3 times 393 kilojoules. Okay? That's what that means. Since NH3 has 3 NH bonds, that's how much energy is going to be associated with NH. Okay? If I look at carbon-hydrogen bonds, the carbon-hydrogen bond energy is 414 kilojoules. Okay, so if I have methane, okay, this is a carbon with 4 bonds to hydrogen that are around it. So this is 4 times 414 to find out the total internal bond energy that's associated with methane. And I know you're all thinking, looking at this and saying, this is absolutely fantastic. I can't wait to stop drooling on my keyboard. Well, you look at these things and you're like, well, that's a lot of information. Now, if I go to something that's a little bit more complex, and I've got these bond energies, guess what? I can use this information to calculate how much energy is inside the reactants, how much energy is inside the products, and from there have a guesstimate or a close estimate of how much energy I'm going to get out of this reaction. Okay? And the way that we run this is from a reaction that's actually pretty versatile. So the delta H of any reaction is going to be equal to the sum of the bond energies in the reactants I hope I don't run out of room. The sum of the bond energies of the reactants minus the bond energies of the products. Okay? So that all that means is that this particular reaction, and I wrote delta H reaction, that's wrong. It's the standard heat of formation, all right? Standard heat of reaction, excuse me, for this particular system. So if I add up the total bond energy that's in the reactants and subtract the total bond energy that's in the products, I'll have a value of how much energy is being released in this system. Now there's something important that needs to be revealed here. And what that is if you look at this and you do this analysis, you'll discover that the energy here and the energy here, when added together, kind of give you the opposite signs for exothermic and endothermic. Okay, if you think about it, my delta H if my energy in my products is lower than that, my reactants, that energy has to go somewhere. And that's because the idea of this reaction, it's a little bit backwards. Okay? this energy over here is the amount of energy required to break the bonds. And over here, this is the amount of energy that's released when those bonds are formed. Because whenever I have a bond formation, it's always going to be a release of energy, because that's a storing of energy that's between those two atoms. So when those two atoms come together, they're going to release energy. If you think about those two hydrogen atoms, when those two things come together, they form a much more stable H2. So when they come together, there's a release of energy when those two get together. So this is required to form bonds. So as a result, the thinking here is a little bit backwards than what you're used to. Okay? So the delta H value that I've got here, the amount of energy required to break bonds, and the amount of energy required to form bonds. So the value that you're going to get here is going to be the opposite sign of what you're used to. Okay? When you add all these values up. But if you think about it, what it's saying is that the amount of energy that is left over if you have less products than you do reactants. Okay? Because you're going to have more energy required to break the bonds. So that means that energy's got to go somewhere. So this is really telling you that it is going to be an exothermic reaction if it's positive. It's a little bit backwards to what we've dealt with already in this particular discussion. Okay? What I like to look at this is when you're doing the bond energies in these two calculations, think of it reversed. Okay? So whenever you get a value here, switch the sign. And when you switch that sign, you'll be able to identify this as how much energy is coming from the exothermic process and how much energy is going away from the endothermic process. Okay? So it's a little bit of a fine point. Okay? But these things are actually very useful if you're trying to determine if a reaction is going to be feasible or not. Okay? Just think about it this way. If my products have a large amount of energy that I've got to put into them, okay, so it's a highly endothermic process, that means I've got to add more and more and more and more heat. When I add too much heat, bad things might happen. Okay? What do you mean by bad things, Dr. Owen? Well, think about it this way. It took a certain amount of energy, in this case 436.4 kilojoules, to separate those two atoms together. If I add too much energy to a system, I run the risk of actually breaking bonds. So if I add too much energy to a system, bad things might happen. I might have decomposition occur, rearrangement of atoms, different things being formed. Okay? If it's too much of an endothermic process, that could be a bad thing. Okay? It's also true on the other side. If I have a very exothermic process, it's a very energetic process. If I do too much of that at once in the laboratory, I might not be around to talk about that later because my entire lab has exploded, right? Okay. Or there's a giant fire that erupts, okay? And then other things might catch on fire. Or, and I just add these two things to a flask, the material might entirely vaporize and shoot material all around my fume hood, which might be bad if I'm breathing that. It might be toxic and I might die. Okay, so there are considerations. There's a very important reason that we talk about this is that they have real consequences when you're doing experimental chemistry and when you're doing the theoretical chemistry, because you have to be able to calculate something and tell other people, this is important because it's got a low energy, we can make it. Or, Joe, your reaction idea is complete garbage because it takes 25,000 kilojoules just to get it started. Okay, these are things that you have to be able to tell people. This is why these discussions are important.